I'm going to be describing this analysis of what is really a subset of the data that you've been hearing about, particularly on the star EV Lacertae, where we happen to have recorded, to some extent serendipitously, both photometry and spectroscopy. The first 8 names on that slide are the people who have contributed actively to gathering the data or being involved in the analysis. And James, as you've heard already, is a professional astronomer at Arizona State University who's published widely on flare stars and has been a great help in guiding us and advising us, mentoring us as we did this project. So there's just a few words about stellar flares. You've heard enough about that already, but maybe I point out a few of the parameters of EV Lacertae. It's about 1/3 the mass of the sun, many times less luminous. Temperature, 3,270 K, so relatively cool, but a fairly fast rotation period of 4.4 days, which has wound up the magnetic field. It means it's a magnetically active star, and that's part of the reason why we're seeing flares from it. It's 5 parsecs away, which a parameter we need to use when we're analyzing the flares. And depending on where you look, which source you look at, its spectral type is somewhere between M3.5 and M4.5, with an E because of the emission, persistent emission output. But it's typical of the fact that stars in this sort of region of the Hertzsprung-Russell diagram, it's really quite hard to be definitive about what spectral type they are. Okay, so our observing strategy. As I say, we're reporting here on observations where we have concurrent spectroscopy and photometry so that we can do a real quantitative analysis rather and do more than we could do with either technique on its own. Our photometric observations are made with typical amateur telescopes, usually with exposures of somewhere in the region of 20 seconds, and mostly with a Johnson-Cousins B-band photometric filter, simply because that optimizes this balance between the flare energy output, which increases steadily as you go to shorter and shorter wavelengths, but our equipment sensitivity is falling as we move into that region. So we're trying to optimize our detection efficiency. The spectroscopic observations that I'm describing here were made with either an ALPI or a LISA spectroscope, auto-guided on similar amateur-sized telescopes with integrated calibration units. And we're integrating these typically for 300 seconds, and which is approximately 10 times the length of a photometric exposure. And what that really means is that our time resolution with spectroscopy is significantly worse than with photometry. Most of our spectra cover the range that you can see there, and we're trying to record accurate timing data in the FITS header, obviously, because we're sometimes synchronizing observations made in geographically distributed locations, but as accurately as possible as we can make it at the same time. So processing the data. Our photometric data was processed by the observer using whatever package they're familiar with, typically either AIP for Windows, MaximDL, or AstroImage-J. Photometry was always uploaded to the AAVSO database, so it was widely available to us. Spectra were processed either with Christian Buell's ISIS software or Shelyak's Demetra, and were all corrected for instrumental and atmospheric losses using a reference star spectra, as you've described many times, to produce relative flux spectra. The spectra were uploaded either to the AAVSO or BAA spectroscopic databases and to our Google Drive that Woody and Bob have described. It really provided a focal point for recording availability of data and allowing us to coordinate our observations to see what each people were gathering and to see whether when you'd got some data, say in spectroscopy, somebody else had been lucky and got the photometry. We performed the analysis I'm going to be describing here with Python software written specifically for this project, but often based on work that had been done on other analysis that we had experience of in the past. Here's a table of the journal of the concurrent photographic and spectroscopic observations. Wake up, whoops. Okay, come back. Watch this guy. That table is in the paper, so you don't need to read the detail, but I just put it up to make the point that it was on 10 nights that we managed to make this concurrent observation, we have the total of just under 40 hours altogether of photometry and just over 40 hours of spectroscopy. And the observers who actually contributed the individual data sets are marked in that table when if you want to go and have a look at it. Okay. And this is an atlas, really, of all of the flares that we managed to record. On those 10 nights, we managed to record 12 flares, which had an amplitude greater than 0.1 magnitude. And we cut off at that in the analysis because we really found that flares that were any fainter than that had too low signal to noise to be able to respond to the kind of analysis we were trying to do. And in fact, only a subset of those gave us really, really good quality results, as you'll see. The first thing we did, because we have a relatively small sample, I mean, the 2 nights had 2 flares on them, so we managed to get 12 flares altogether. The first thing we did was to eyeball these. We have a sufficiently small sample that we can rely on that as a way of analyzing them. If you're dealing with a very large sample, you have to automate that process. So we were able to be fairly subjective in deciding whether a flare was there in one of the data sets and when it started and when it finished. And thereby also identify parts of the light curve where there was no activity, which we would describe as the star being in quiescence. Once we'd identified that and documented when the stars when flares started and finished, we could then use that to analytically analyze the rest of the data about the flare. Okay, and just to give you an idea of the kind of range of flare behavior we see, it's very wide. The horizontal timescale on these plots is the same in each case. And it's a real contrast between, on the bottom, a very impulsive flare, which goes up and comes down very rapidly, reaches a very high, that was almost two magnitudes in amplitude. The top flare was very lethargic. It crept up, it bubbled around a bit and slowly went back to close to quiescence, but it was a relatively small flare. And that's typical of the range of flares that we're observing. And we're trying to do a consistent analysis across all of those morphologies of flare, which is itself quite difficult. And here's a table, again, one in the paper, which just lists the parameters that we were able to measure for each of those 12 flares. I would just draw your attention to the fact that the mean rise time we found was about 5 minutes, and it was fairly narrow distribution. These tend to be whatever they eventually do after they reach a peak. They do tend to rise relatively rapidly, but the decay time range is very large. The mean there is about 60 minutes, but some of them are only 30 minutes. Some of them are 2 hours long almost. So a very wide range of decay. The energy, the B-band energy, which I'll be describing in a minute, how we've calculated, the mean of that, taking it as a log to the base 10 of the energy, is 31.7. And there are a couple of methods that are used, widely published in the literature, for assessing the duration of a flare, which are a little bit less dependent on the subjective judgment of when a flare starts and finishes. One is the T1/2 parameter you've heard about already, which is effectively a full width half maximum. And that average is about 5.2. And the equivalent duration, which is another analytical way of assessing the flare, has a very similar value. So all of these assessments of the flare behavior are relatively consistent. And I would just also mention the final column there is for 3 flares, for the 3 brightest flares that we had, we were able to make an assessment of the black body temperature in a way which I'll describe. Okay. Calibrate an absolute flux. That was the key thing we wanted to be able to do by having both photometry and spectroscopy. We were doing this either with data that had been obtained at a single observatory where people had the ability to do that, or by remotely coordinating people working at different locations. The key to this is that our B-band magnitudes are in effect measurements of the absolute flux of the part of the spectrum transmitted by the filter. As those of you who were at the workshop a couple of days ago will know, that we have a methodology for doing that. And we were able to use that to calibrate our relative flux spectra in absolute flux units of ergs per square centimeter per second. And that the diagram at the bottom is just to show you what a relative flux, typical relative flux spectrum of EV Lac in quiescence looks like, and where the B band filter pass band fits in respect to that. So we were essentially measuring the flux transmitted through that B filter when we talk about the B band flare energy. And this is, remember, it's specifically the energy of the flare in the B band. We're not trying to do bolometric assessments of the total energy of a flare in this analysis. Okay. So here I've taken as an example the largest flare that we recorded on the 21st of November. In the top plot, in gray is the mean quiescent spectrum that we observed before the flare went off. And above it, I've shown the peak flare spectrum. So that was the spectrum recorded at the highest point of the flare. And you can see that what happens during the flare is essentially that the blue end of the spectrum rises. The energy is being emitted increasingly towards the blue end of the spectrum. There is relatively little change in the H alpha line, which is perhaps a problem of just measuring H alpha on its own. But you can see that the higher order Balmer lines, beta, gamma, delta, and epsilon, increase substantially more during the flare. And on the bottom plot is the difference between the two lines in the upper plot, which is the flare-only spectrum. That's the energy, and the vertical axis is now calibrated in absolute flux in ergs per square centimeter per second per angstrom. So you can see that the Balmer lines really are very prominent, but we're also starting to pick up small levels of emission in helium-1, magnesium-1, and possibly also in helium-2, and certainly in calcium-2K. So that we're able to pick up emissions in wavelengths other than just the Balmer lines in really the more energetic of the spectra. And this is how we try to work out the black body temperature. We take the flare spectrum and identify 4 regions in it where there are no emission or absorption features, and then fit the Planck black body temperature profile or function to just those 4 regions of the spectrum. And that gives us a value for the black body temperature. In this case, it was just under 19,000 Kelvin. On the other 2 flares that we recorded, we were able to make this measurement reliably. They were at around about 10,000 Kelvin. Again, the numbers are in the paper, which is interesting because in a lot of the published literature, when people talk about the black body temperature of the flares, it's often assumed that they have a black body temperature of about 9,000 Kelvin. And in fact, we've shown that we were able to pick up flares that are significantly brighter than that. But it's also true that for the other flares, the other ones other than these 3, we really were not able, the flare spectrum was not clean enough and well-defined enough to give us reliable temperature measurements. So it's not a particularly easy parameter for us to measure with our sort. Okay, so how do we measure the B band energy in a flare? That's what we're actually trying to get to. So you start with the measured B band magnitudes, and the upper plot there is simply the magnitude plot of the B band magnitude plot of that bright flare on the 21st of November. We convert each B band magnitude to an absolute B magnitude using the distance modulus. So that's taking the magnitude back to where what you would measure if you were actually close to the star itself. We convert that to a B band luminosity in ergs per second using the solar luminosity in absolute magnitude parameters, just basically to scale from magnitude to luminosity. We subtract the mean quiescent B band luminosity to get the flare only B luminosity. That's what we're trying to measure, just what's the energy being emitted in the flare. We can then integrate that over the duration of each magnitude measurement. Say that was 20 seconds. It's being during that whole 20-second period. And that gives us a contribution to the B-band energy in flare energy in ergs. And then we add up all the contributions from all of these magnitude measurements to eventually get the total energy which was recorded in the B-band for the flare in ergs. And in this case, the value was log 10E was 32.6 ergs. That, as I mentioned, was the most energetic flare that we were able to record. So that's how we work out the B-band flare energy, which is tabulated in the paper. And what we also want to be able to do is because these spectra are calibrated in flux, we can start looking at the energy in the individual emission lines being produced. So in the plot on the upper right, we've got at the bottom the quiescent spectrum around the hydrogen beta line, and above it, what happens during the flare. The line rises substantially. The continuum goes up by maybe a factor of 3 or 4 in flux, and the flare gets substantially stronger in the line. So what we need to do is subtract the mean quiescent spectrum, that's the bottom line, from the hydrogen beta line in the flare to get the energy, the flare only spectrum of the hydrogen beta line. And that's really what you see in the lower right there. We want to interpolate the continuum under the line, because what we were really trying to find is what is the energy in the flare above that background continuum. And that's the area that's shaded in yellow on that plot. So we subtract the interpolated continuum to get the flux in the line. We then integrate that flux over wavelengths to get the total, that's the total area of that flare. And then that gives us the flux in the line in now ergs per square centimeter per second. We've got rid of the angstrom. We can then integrate that over the duration of each spectrum, which typically 300 seconds, to now get the contribution to the luminosity of the line in ergs per square centimeter. So we're gradually trying to, using all the information we've got to accumulate this picture of the total energy. And then we have to, if you want to find the total energy being emitted in the emission line, we have to multiply by 4 pi d, which is your 5 parsec distance, because you've got to integrate over the whole solid angle around the star to find out the total energy that was being emitted in the flare. And in this case, log E was 31.7. And if you remember what it was for the total B-band energy, this is about 1/10 of the energy which was being emitted in the flare in the B-band as a whole. So that because we have this data, we're able to quantifiably analyze the data to get numbers like this out. If you start looking in the professional literature, you find that there's not many cases do they quote energies in absolute units, because it's often they don't have flux calibrated spectra. They have to quote flux ratios or work with normalized spectra. So we have got something, I think, that's scientifically useful in the data that we have. And here's just a table, again, you'll find it in the paper, for the energy, doing this calculation for each of the lines, hydrogen emission lines for each of the spectra. And we can do that reliably in most cases. There are a few blanks where the data just wasn't up to the calculation, but that gives us the energy for each of these lines. Now, hydrogen beta to hydrogen epsilon lines all lie within the photometric B band. So it's quite interesting. If you average over all of these flares, just to get an over picture, the total flare energy emitted in these lines is approximately 40% of the total flare energy emitted in the B band. So in other words, what we're saying is that of the energy emitted in the B band, about 60% comes from the rise of the continuum level, just the general increase across the whole continuum, and about 40% is the additional rise above that in the emission lines. Again, I think that's a useful thing for us to be able to say. So because we're quantifying this, we also have a responsibility to try and quantify the uncertainties. We've got to understand just how well are we being able to measure these things. And if we think about it, we really, the uncertainties can propagate in from several sources. One is the uncertainty we have in measuring and estimating the mean B magnitude used to flux calibrate each spectrum. And that we have to work that out, because we have a series of short duration B magnitude measurements. We have to turn those into fluxes, integrate them together, turn them back into a magnitude to get an equivalent magnitude for flux calibrating that spectrum. And there's an uncertainty that propagates through that process. There's also, we have to have some feeling for what is the uncertainty in the continuum level in the spectrum. Now, it's fortunate that we have, in most of these spectra, fairly long periods where there's quiescence, and we can use these quiescent spectra and say these are effectively multiple measurements of the same quantity to work out what is the uncertainty at each wavelength in statistically in being able to measure a spectrum of the star. And that gives us a handle on just how well we're measuring continuum flux as a parameter. And then when we get to measuring the flux in a line, because we're interpolating across under the line from the continuum at the side, there's an uncertainty in how we're determining that continuum. So all of these quantities that we're trying to measure come along with an uncertainty in how much we can measure them. So we try and propagate these together and compute a statistical uncertainty based on the variability of the data. In the plots I'm going to show you in the next plot, next slide, I'm going to represent those by bands of uncertainty on the quantities. So along the top row, we've got the hydrogen beta, hydrogen gamma, and hydrogen delta lines on the 21st of November, when we had the very bright flare. Each plot shows you a continuum flux, and what that is a measure of the continuum flux adjacent to the hydrogen beta line. So it's just the measurement of the continuum very close to the hydrogen beta line, and the red graphs are the flux in the line itself. Now, what you can see, for example, is how quickly the continuum goes up and then goes down again. Very, very quickly after the flare, the continuum level of the spectrum drops much more quickly than the energy goes out of the emission lines. And also you can see that as you go to shorter and shorter wavelengths, the line flux also diminishes. But what you can also see on that is that there's a time lag between the peak in the continuum flux and the peak in the line flux. It's a very tricky thing to measure with spectra which is 300 seconds long, because your time resolution is very poor. And it's a matter of luck in a way, whether one peak falls within one 300-second spectrum and the next one falls in the next 300-second spectrum, which did happen for the top line. The bottom row, which is the spectra analysis of the spectrum recorded on the 26th of November, where actually we had two flares, a very small one and then a much bigger one. We were not able to resolve the peak in the continuum flux, in the continuum rising, and the flux in the lines themselves rising. The better we can resolve in time our spectra by taking shorter exposures, the more we'll be able to say about what that real lag is. It's clearly documented in the literature. There is a lag between the peak of the continuum and the peak in the Balmer line, and that's very much related to the physical processes that are happening in the star, where there's an initial great burst of energy across the spectrum, and gradually the excitation in the hydrogen gas in the chromosphere decays away more slowly. James will probably be able to say a lot more about that than we can. Okay, and what this shows is that if you look at the energy in each of the lines going from hydrogen beta to hydrogen epsilon, there is a steady deterioration or degradation in the energy emitted at each of those wavelengths in all 12 of our spectra. It's a very consistent picture that most of the energy goes out in hydrogen beta, and then it gradually is less and less towards hydrogen epsilon. This confirms behavior that's been seen in many papers, but we are here quantifying it in an absolute sense, which is something that I think is not always able to do so easily in the professional data where they don't have the calibration in absolute flux. And another measurement here that I think Bob mentioned was this T1/2, which is full width half maximum of the peak in the Balmer lines. And then also, as you go from hydrogen alpha through to hydrogen delta, you see that the duration gets less and less. The peaks are much wider and last longer in hydrogen alpha than they do in hydrogen delta. Again, that's something that's seen very much before and published. And just to compare our data with what has been published, the plot on the left is the same one as just showed you before, but flipped around horizontally. So I can compare it with the plot on the right, which is from a paper Kowalski wrote in 2013. It's almost identical data in the measurements of the half widths of the lines. So in summary, I would just say that working as a collaborative group, we've observed 12 moderately bright flares of EV LAC, where we have been able to record currently spectroscopy and photometry. We've been able to calibrate the spectra in absolute flux and calculated the B band flare energies in that range. We obtained flare-only spectra by subtracting mean quiescent spectra, and by doing that, we were able to calculate the energy emitted in the bar for each flare. We could measure Planck black body temperatures for the 3 brightest flares. We observed evidence that luminosity of the continuum does peak before the Balmer emission lines, and it decays faster. And also that higher order Balmer lines had lower energies and decayed faster than the lower order Balmer lines. That's what we've seen in the last 2 slides. And I think our results confirm that behavior seen in professional studies, because we have simultaneous, sorry, should have showed you that before. Because we have simultaneous spectroscopy and photometry, we're able to quantify these results in absolute luminosities and energies. So I'll just leave that up for a minute so you can have a look at it. Okay, just some acknowledgements to both the AAVSO and the BAA who've provided us with the infrastructure for storing our data. The AAVSO produces many other useful resources. You'll all be familiar with NASA's ADS because that lets us get the papers, the professional literature that we need to assess our data, and also CDS for providing SIMBAD, which is a very useful tool. The developers of AstroPi have really made it possible to produce analyses like this much more easily than if we hadn't had that as a resource. The BAA has helped me to come here, so I thank them. But most of all, really, my colleagues who've provided an online environment during COVID, which has really nurtured this project, got it off the ground and enabled us to produce the sort of results that we're able to tell you today. So, thank you for listening.
Okay, there's some questions. We'll do this rather quickly because we're over time.
Yeah, I'm sure I'm between you and your lunch, so.
So physically, the decay, the faster decay and the higher energy lines, isn't that physically exactly what you would expect if it was just a pure black body radiation that was cooling over time, and so the higher wavelengths cool more quickly? And
yes,
you know, it's quantized because it's the spectral lines, but
right,
it's just cooling. Sorry.
Yeah, but the behavior of the continuum is different from the behavior of the lines. You can see that.
Okay, real quick too, the what's the analog, the slow decay of some flares versus the fast decay of other flares? What's our solar analog, or is there one, since we have such different systems, such different stars?
Us. Yeah. Ask James when he talked.
Right, online, Tom Smith is asking, have you seen a relationship between flare energy rise to the width of the flare at its peak? The H beta emission line energy measurement slide is what he's referring to there.
Okay.
So I guess we can try to
Can
get
you-
back to
can you
that.
get back to-
Well, let me try to get back to that. while
Okay,
you try to-
you get that.
Yeah,
Hmm.
we wanted to stop. No, it was, I think we're past.
Yeah. So the next one, that one. Is that what he's referring
No.
to?
I'm not sure, but I'll try to answer it. Have you seen a relationship between flare energy rise to the width of the flare at its peak? Let me see if I can find that slide while you answer it.
Yeah.
No. Yeah,
Probably
that
the
one
best
is-
source of that information is to look at the tables in the paper, because you can see then whether what the rise time was for individual flares and also the decay time. We've tabulated there as much of that information as we were able to gather from the data itself. I hope that gives
Yeah,
you
my guess
an
is he's
answer,
referring
Tom.
to what's in the paper. Yeah, when you don't have.
Yeah.
Just real quickly, look like your descent back to the quiescent line after a flare is at a higher level than before the flare occurred. Is that?
That's very often the situation, which makes it very hard to say when a flare is finished. And also, they very often run off the end of the observing run. So your flares seem to take a long time. Most cases take a long time to decay. They may even come down pretty quickly, but then they tail off. And this is
eventually
interesting, the way that the professionals try to parameterize them. There are various models to try and capture that behavior.
Eventually return to that quiescent line before the flare always, or is there a case where
Well,
they don't do that?
I suspect it will eventually, because the activity in the chromosphere will die down and it will return to quiescence.
Let me just add to that. There are some nights when there's a lot of activity. We see a lot of small flares. And so, and a lot of times you'll get a flare and then you get another one and it just hasn't had time to get back to quiescence again.
Mm.
So, and I think that might actually have something to do with the funny shape of some of those flares, is that we
Yes.
might be seeing 3 or 4 small flares. We have one night where we argued about, was it 5 or 6 flares, because it was
Yeah.
burbling as we
Yeah,
talk.
it could be there's some kind of connection between the processes where one flare then triggers another one, and you get a sequence like that.
Okay, thank you so much.